Hello, my name is Shlok Pandey and I will be presenting my ELP 101 project on radio circuits. So the main component of radio circuit which I will be explaining is how the radio circuits tune into the exact frequency of the signal waves which are broadcast by the channels. So this involves some very fundamental concepts of electrical engineering and AC in specific. So the first one is the variation of reactance of inductor and capacitor with frequency. The second one is the main part, which is resonance. And the third part of the project has two subparts. First is how the device actually detects signal, and the second part is the properties of resonance, which are bandwidth and quality factor. And combining all these fundamental AC circuit concepts, we can understand the design of the tuning mechanism of radios. So the first part, the reactance of capacitor or inductor relates the value of the voltage across the device and the current which is flowing through it. It is like a measure of opposition which is offered by the device to the current which is flowing through it. And unlike a resistance, a reactance is not independent of the frequency of the source. It depends on the source along with the material with which it is made. And the formula for the impedance or reactance of the capacitor and inductor are this. So this is a purely capacitive circuit, and as we can see, the current through the circuit leads the voltage applied across it by 90 degrees. Here we can see that the voltage leads the current and the current lags to it by 90 degrees. And if we plot it on a phasor diagram, we can see that if we take the 90-degree axis as the imaginary axis, the capacitive reactance is given by minus j by omega c, and the inductor's reactance is given by j omega L. So now coming to the net impedance of the RLC circuit. So as the individual impedances of L and C depend on frequency, thus the net impedance also depends on frequency. And RMS value of current is given by IRMS equal to VRMS by ZNet. And we can see from the formula I is minimum when ZNet is I is maximum when ZNet is minimum. And at resonance, at reactance of capacitor is equal to that of inductor. So this is the main criteria for RLC resonance, and where the net impedance is purely real and there is no imaginary component. And we will see the derivation of this omega net in the next slide. So calculation for resonant angular frequency omega naught. So this is the basic phasor diagram of any RLC circuit, and we can see that the Z net is given by square root of R squared plus XL minus XC whole squared, and the phase angle phi is given by tan inverse XL minus XC by R. So at resonance, XL is equal to XC as we have seen from the previous slide. So Z becomes equal to R, which is purely real. XC is equal to XL, and phase angle is equal to 0. And if we put the values uh, of omega of XL, which is omega L, and XC equal to 1 by omega C, we can easily see that omega is equal to 1 by root LC. And this is the phasor diagram for resonance, where we can see that the XL gets completely cancelled by XC. Now, coming to the third part's first subpart about how the detector actually detects these signals, which are in the form of radio waves, which are broadcast by the broadcasting channels. So the radios have antennas which receive these various radio waves of various different frequencies broadcast by different channels. And when we turn the tuning knob of the radio, we change the value of the capacitance in it. And because of this, the value of 1 by root LC, which is omega, also changes because C is changing. And this altered resonant frequency matches the resonant frequency of one of the input signal out of the various ones. And when this happens, a significant amount of current flows through the circuit, and through this current we can derive information through about the signal and then convert this digital information then into audio output. Now the second subpart is the properties of the resonance. So two of the properties are power output in the RLC circuit and bandwidth. So power in RLC circuit is given by this formula, which is just IRMS squared into R, and simplifying we get this. And at resonance we can see XL is equal to XC, so the value is just VRMS squared by R. And bandwidth, now coming to the second property, refers to the range of frequencies around the resonant frequencies where the power P is greater than half of the power output at resonance. So we can see from the formula for P average that when XL minus XC squared is equal to R squared, it will be VRMS squared R by 2R squared, which is P naught by 2. So writing this, we get XL minus XC squared is equal to R squared, which is a quadratic equation. And solving this, we get the roots omega 1 and omega 2, and 2 pi f is equal to omega. And from there we can get f1 and f2, and the bandwidth is as shown in this figure. Now coming to the most important property of resonant circuits, which is the quality factor. The previous slide's quadratic equation on solving and taking the difference of the two roots omega 2 and omega 1, we get delta omega equal to R by L, which is the bandwidth. And the quality factor is defined as Q is equal to omega naught by this bandwidth delta omega. Now the circuit has higher selectivity if it is narrowly peaked. What selectivity means I'll just come to in a minute. And we can see Q is equal to omega naught upon L by R, just putting the value of delta omega is equal to R by L. And we can see from here that Q is inversely proportional to R. So as we can see in the diagram here, R1 is less than R2, therefore Q1 is greater than Q2, and we can see that Q1 has higher selectivity. So higher selectivity basically means that the resonance circuit selects the frequency, selects as in if the frequency of the input is close to the resonant frequencies, then huge amount of current is drawn to the circuit and the power output is also large. Whereas if the frequency differs by the resonant frequency by some amount, then the power output, as we can see from the graph, is negligible, and thus the disturbance in the signals is also less, and thus the final output of the quality of sound produced is also higher. So the circuit which so the graph which is has a narrow peak is preferred over this other graph which has a wider peak and is shorter. And that's it. Thank you.